Hi, Perculus Honors. So these are notes 9.3. So go ahead and take a minute to read the objectives. Go ahead and pause the video and read through our 7 objectives for today. We are studying sequences. A sequence is an ordered progression of numbers. So an infinite sequence is a function that assigns a unique number, a sub n, to each natural number, n. So let's look at some examples of sequences. To take a look at A, B, C, D, and E, and just go ahead and see if you notice any patterns with each of those sequences. Go ahead and pause the video and take a minute to look for patterns. Okay, so notice the first sequence is finite because it does not have these 3 dots that indicate that it keeps going. So B is infinite. There will be infinitely many terms in this sequence. Notice that the pattern here is you are adding 5. The pattern here, notice it might help if you think about the first term. If we think about, think about notation. When we say a sub n, you could describe the nth term in the sequence. So notice when we say natural numbers, we're starting with the first term will be n equals 1. The second term is n equals 2, etc. n equals 3. So that might make you actually even notice that there's a pattern here, that is n squared, right? Because we have 1 squared, 2 squared, 3 squared, etc. So notice this next part, part C, we could describe a rule. You could say that this one gives a rule that defines the kth term. The kth number in the sequence is 2 to the k power because the first term was 2 to the 1. Then we have 2 squared, 2 to the third, etc. So that would be for, again, we used n. I talked about n in B. Now we're saying k is 1, k is 2, k is 3. Take a look at part D. For part D, this gives a rule that defines the nth term. So we could say the nth term, a sub n, is 1 over n. So you could say, well, that would be 1 over 1, 1 half, 1 third, 1 fourth. And again, those 3 dots indicate that it's infinite. It keeps going. So this notation for part E, we're describing the first term, a sub 1, the second term, a sub 2, etc. Notice the nth term is out here. So the term after the nth term would be the n plus 1 term. The term before the nth term would be the n minus 1 term. Notice here I asked you, how would you describe the term after a to the n plus 1? Well, again, we have the first term, the second term, the third term, etc. You could have the nth term. After that would be the n plus 1, the n plus 2, etc. Okay, so again, the infinite sequences, which is what we're going to focus on, would have the 3 dots indicating that it's an infinite sequence. So for number 2, now we're going to talk about explicitly defined sequences. So I ask you to find the first 3 terms and the 100th terms of the sequence a sub n, in which a sub n is equal to n squared minus 2. So you could say, I would like to find the first term. So we'll let n equal 1. So the first term is negative 1. I'd like to find the second term, n equals 2. So over here I probably should have said for n greater than or equal to 1, because again, we're using natural numbers. I wouldn't ask you for the negative 5th term or the 0th term. I wouldn't ask you for the 1.5. It would be the first term, the second term, etc. So now we have the second term is 2. And let n be 3, and you could find the third term is 7. So you could write negative 1, 2, 7. There we go. And it might be kind of hard right now if you wanted to think about the 100th term, but you could just let n be 100. So the 100th term is 9998. So the next thing we need to talk about is a recursively defined sequence, and then we're going to compare and see how the explicit and the recursive looks different. So first of all, why don't you pause the video and think about how does this particular explicitly defined sequence look different from the recursively defined sequence. Okay, so for this number 3, for the recursively defined sequence, they told us the first term was 3, and then this notation is saying that any term, the nth term, is equal to the term right before that, the a to the sub n minus 1 term plus 2. So the next term you would take 3 and add 2. To generate the next term, you'd say 5 plus 2 is 7. And again, because you would say, for example, if n is equal to 2, you could say a sub 2 equals a sub 1 plus 2. And that's how we get that a sub 2 is 3 plus 2, etc. So notice this is saying that the nth term is equal to the n minus 1th term plus 2. Okay, so again, we could generate some terms. Now, this one might be tougher to think about the 100th term, because you might say, well, might you tell me the 99th term? Because then I would know just to add 2. But think about what we did. We started with our first term, and if you're adding 2 for the 100th term, wouldn't you add 2 99 times? So you could find that the 100th term is 201. Okay, so let's think about how these are different. So the explicit, notice for the explicit formula, if I wanted to find, for example, the 100th term, I just let n be 100. But over here, each term is defined by using the previous term in the sequence. So the recursive formula is relating each term to a previous term in the sequence. So that's how they look a little different. Notice we have a sub n on the left side of the equation, and we have n over here. And for the recursive, you would have to define your first term, and you would describe how each term would be could be related to a previous term, and then you would also have to say n greater than 1, because again, you wouldn't ask for a negative term or the 0th term. You would start with the first term. Okay, so this is a very famous sequence. Go ahead and pause the video and think about how might you describe this particular sequence recursively. Okay, so this is famous. This is the Fibonacci sequence. Notice to generate more terms in this sequence, you would say 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, etc. So 5 plus 8 is 13, and 13 plus 8 is 21, 21 plus 13 is 34, and it's an infinite sequence. So if you wanted to describe this, I think it would be not so hard to do this recursively. You would have to define the first term, the second term, and then each term is equal to the sum of the two terms before it, and you would have to say n is greater than or equal to 3 and for positive integers. Because again, I wouldn't ask you for the 2.3 term or something like that. It would be the first term, the second term, the third term, etc. Okay, so the next thing we need to talk about are arithmetic and geometric sequences. There are many kinds of rules to construct sequences. Arithmetic sequences have a common difference, and geometric sequences have a common ratio. So pause the video and go ahead and read about arithmetic sequences and geometric sequences, and then try and give an example for each. Okay, so if we're thinking about an arithmetic sequence, notice we have some common difference that you're adding the same number. So for the example that I have, I've made my common difference 3. So if I keep adding a common difference of 3, this is an arithmetic sequence. Notice for number 6, I made an example and I made my common ratio 10. So I keep multiplying by 10. And so again, it's a geometric sequence if you're multiplying by a common ratio, a non-zero common ratio, r. So in an arithmetic sequence, each term can be obtained from its preceding term by adding d, and each term, and for a geometric, can be obtained recursively if you would like to do multiply the preceding term by r. Okay, for the next example, for number 7, we were going to try and define each sequence explicitly. So you're going to try and find a rule for each sequence. Try to define it explicitly. Go ahead and pause the video. Describe the nth term, please. So if I had to find an explicit rule, I think the first thing I would do is to try and decide if it was arithmetic or geometric, because notice I had some formulas that I could use. But for this one, number 7a, I noticed that it is not arithmetic because 1/2 minus 1 is not the same as 1/3 minus 1/2. It's not geometric because 1/2 divided by 1 is not the same as 1/3 divided by 1/2. But I do notice that if the first term is n and the second term is 2, etc., that you could describe this as a sub n is equal to 1 over n. So now if I wanted, for example, the 100th term, I would just let n be 100. For the next sequence, this is also, b is not arithmetic and not geometric because 1/5 minus 1/3 is not the same as 1/7 minus 1/5. If you check that on your calculator, you will see that they're not the same, and it is also not geometric because 1/7 divided by 1/5 is not the same as 1/5 divided by 1/3. So you could even check it on your calculator. Again, each term, in order to be arithmetic, you would have to be adding a common difference. But again, 1/5 minus 1/3, not the same as 1/7 minus 1/5. To be geometric, there would have to be a common ratio. But again, 1/5 divided by 1/3 is not the same as 1/7 divided by 1/5. I do notice that the numerator in all of these fractions is 1, and the denominator reminds me of an arithmetic. So again, even though the sequence is not arithmetic, it looks like the numbers in the denominator are, so that might be helpful because we know that for an arithmetic sequence, you could use this formula. So here's our recursive rule, and then we would have the first term plus n minus 1, or d's, so to get the nth term. So here is our explicit rule. So you would have 1, a sub n equals 1 over the quantity 2n plus 1. Let's take a look at part C. So the first thing you would think of is C arithmetic or geometric, and you realize it's not. So you might want to think about how you might describe it. We have the first term is 2, the second term is 5, the third term is 10, etc. So you might notice that the nth term could be described as n squared plus 1, which again is not either arithmetic or geometric. Go ahead and take a minute and try and think about how you would describe D explicitly. And again, if we don't have a formula, this might take a while. Go ahead and think about it. How might you describe the terms in that sequence? So for D, that was also tricky. I was looking at the way that the terms alternate their sign. So if you have negative 1 to the nth power, notice that if n is 1, you would have a negative for your first term. If n is 2, a positive term for your second term. And notice that if n is 1, the denominator in that first term was 2, and then 4, and 8, and 16. So 2 to the n would describe the denominator. So what we're going to do now is, again, we're going to realize that we have a formula for arithmetic. We need to talk about our formula for geometric. So what we're going to do is we're going to just decide by looking at these sequences, are they arithmetic, geometric, or neither? So we do have a formula sheet, but before we move on, we should probably talk about the formulas that we've discussed so far. So for arithmetic, we have a recursive formula, and we have an explicit formula. For geometric, we talked about our recursive formula, but we should also talk about our explicit formula. If we wanted to describe our geometric sequence explicitly, the nth term would be the first term times, again, n minus 1 r. So you'd have to multiply that first term by r n minus 1 times. So now we have some formulas to think about. What I would like you to do is think about each one of these sequences and decide arithmetic, geometric, or neither. So go ahead and pause the video and do that now. All right, why don't we talk about A and D, because they were neither. So if you wanted to try and think of how you would just define this explicitly, that might take a while. Again, you might think, well, this is the first term, this is the second term, third term, etc. So the nth term is 3 to the n minus 1. But I think it would be a little trickier because you don't have the formulas that you would be able to use with the arithmetic and the geometric sequences, because A was not arithmetic or geometric, just like D, not arithmetic or geometric. But what you notice for D is that the numerator, actually, if you just thought of those numbers, was a geometric sequence, and the denominator was an arithmetic sequence. So you could consider the numerator and denominator temporarily, just consider those separately. So for the numerator, here's our formula to describe an arithmetic sequence explicitly. So the nth term would be the first term plus the common difference. I'm sorry, and this is the denominator because the denominator is arithmetic. So it would be the first term was 3 plus the common difference d. So to describe the denominator, it would be 2n minus 2 plus 3, which is 2n plus 1. And if you wanted to consider the numerator, you could use the formula a sub n equals a sub 1 times r to the n minus 1. So that would be the first term 1 and the common ratio. Notice you're multiplying by 2. So for D, you could describe the nth term as 2 to the n minus 1 divided by 2n plus 1 for n greater than or equal to 1. Well, and now that we have our awesome formulas here, why don't you pause the video and take a minute and see if you can find an explicit rule for B, C, E, F, and G. Go ahead and give it a try. There we go. So those are explicit rules for each of those arithmetic and geometric sequences. Now, what you might want to think about before we move on to the next example is notice that we had we had four of these sequences were geometric, and it's kind of interesting that B, the signs alternated. C, the signs of the terms, they're all positive. E, they were negative, all the terms were negative. And then F, they also alternated. So again, very interesting about the geometric sequences. Depending on if the first term is positive or negative, and if the common ratio is positive or negative, the terms could alternate. They could all be positive, they could all be negative. When I say alternate, I mean alternate signs. What we're going to do next, we're going to find an explicit rule and a recursive rule for the nth term of each sequence. So one sequence is arithmetic, one sequence is geometric. Go ahead and use the formulas that we have up here, that we kind of derived from thinking about what it means to be arithmetic and geometric. And go ahead and find an explicit rule and a recursive rule for the nth term of each sequence. So here we go. Here's our explicit rule. For arithmetic, we have a sub n equals 7n minus 4. Now for the recursive rule, notice that you have a lot of elements that you have to make sure you have. You have every term is the term before it, the previous term, plus 7, which is the common difference, and you have to say for n greater than 1. You could have also said n greater than or equal to 2 because we are talking about integers. And notice you have to define the first term. Over here, I said that our explicit rule for the geometric was a sub n equals 120 times the common ratio, the n minus 1 power. Recursively, any term is the term before it times the common ratio, which is 1/2 for n greater than 1, and the first term is 120. Notice for a recursive, you also could have said the a to the sub n plus 1 is equal to the nth term, which would be the previous term, times 1/2. You would just have to adjust then and say for n greater than or equal to 1, and the first term is 120. So notice for recursive, you certainly need to give the first term. So we have two challenge problems here. Let's try 11. It says, write an explicit rule and find the 10th term for an arithmetic sequence with the second term is 8 and the sixth term is 24. So let's go ahead and pause the video and think about how could you find the common difference if you're given the second term and the sixth term of an arithmetic sequence. It told us it was arithmetic, so to find the common difference, we do 24 minus 8, but it took 4 steps to get from the second term to the sixth term. So we would divide by 6 minus 2, which is 4. So the common difference is 16 divided by 4. The common difference is 4. Let's just test that out and see if that worked. 8 plus 4 is 12. 12 plus 4 is 16. 16 plus 4 is 20. And again, you would back up to find the first term. So if we want a rule, we would say that the nth term in an arithmetic sequence is the first term plus the common difference times the quantity n minus 1. Let's go ahead and try number 12. This time we have a geometric sequence. Go ahead and pause the video and think about how you would find the common ratio r if all you were given was the second term and the sixth term in a geometric sequence. All right, so we need to find out what you're multiplying by in one step. Well, in 4 steps, we're multiplying by 2.5 divided by 40, so the common ratio is 2.5 divided by 40 to the 1/4 power, because again, it took 4 steps to multiply by 2.5 divided by 40. So our common ratio is 1/2, but actually, notice our common ratio could be positive or negative 1/2 because we were only given the even numbered terms. And notice we talked about how a geometric sequence, all of the terms could be positive, all of the terms could be negative, or the signs could alternate. And notice we were not given an odd and an even term, so perhaps those odd terms with this limited information could be negative. So we would have to consider that the r could be positive or negative 1/2. Let's just check our work here. If we divided 40 by, or if we multiplied by 1/2, by 1/2 by 1. And that, if we went backwards to find the first term, we'd have to multiply by 2. So you could say that for a geometric sequence, here's our formula. We could say that the nth term is the first term times the common ratio to the n minus 1. But notice if our common ratio was negative 1/2, our first term, the odd terms, would be negative. So you would say a sub n would be negative 80 times negative 1/2 to the n minus 1. Okay, so we're talking about the end behavior of sequences. So we're thinking about if you have a sequence of an infinite sequence, you have a sequence of a progression of numbers, what is happening as n approaches infinity for a sub n. So your sequence will either converge, so it will approach some number, or the limit of the sequence, if it's infinite or non-existent, there is no limit, then the sequence diverges. So let's just look at a couple examples and think about this. So go ahead and pause the video and think about those first two sequences in A and B. Okay, so first of all, did you notice that A was kind of a trick? This is finite. So it does not converge or diverge because it's not infinite. But if we're thinking about B, for example, notice that if you're thinking of the limit of 1 over n as n approaches infinity, because that's how you could describe 1 over 1, 1 over 2, etc. Notice that that converges to 0. Sequence converges to a limit of 0 because for large values of n as n approaches infinity, that number would approach 0. 1 divided by a very infinitely large number would be 0. Let's think about part C. Go ahead and pause the video. It might help actually if you think of an explicit rule. So actually this is a sub n is n plus 1 over n. And maybe that might have taken you a few minutes to think about that. Think about how what would happen for as n approaches infinity. So it might help if you use your calculator. Notice we have y equals the quantity x plus 1 over x, and I just looked at the table. So I'm trying to think of what would happen as n approaches infinity. So for large values, I started with 10, then 100, then 10,000. Notice that the limit, the sequence converges to a limit of 1. Let's think about the next example, part D. So notice it's an infinite sequence. We're going 2, 4, 6, 8. Next would be multiply. I'm sorry, you're adding the common, this is an arithmetic, your sequence, you're adding 2. So 2, 4, 6, 8, 10, etc. So notice that this sequence diverges because the limit is infinite. The sequence just gets larger and larger and larger as n approaches infinity. Notice that that term would just approach infinity, so it diverges. Let's think about E. Notice this sequence is oscillating between values. There is no limit as n approaches infinity for a sub n. So notice the limit of the sequence. If the limit is infinite or non-existent, the sequence diverges. For F, this one diverges, but for a different reason. Notice that the limit is infinite. For F and G, as n approaches infinity, n squared plus 1, and for F and for G, e to the n, that number will approach the terms in the sequence will get larger and larger, so those sequences diverge. The limit is infinite. So what we need to talk about for H, J, and K, we have to remember what we've learned about rational functions and horizontal asymptotes. So go ahead and pause the video and think about H, J, and K. Okay, so thinking about what we remember from rational functions and horizontal asymptotes, for H, the degree of the numerator and denominator are the same. So the horizontal asymptote would be at 2. So we know as n approaches infinity, for a sub n, for H, the sequence converges to a limit of 2. For J, the degree of the numerator is less than the degree of the denominator, so there'd be a horizontal asymptote at y equals 0. So the limit of the function as n approaches infinity would be 0. The sequence converges to a limit of 0. So for K, the degree of the numerator is greater than the degree of the denominator. So this sequence, we know that as n approaches infinity, this sequence diverges. And for our last example, you might think about how this is described recursively. So you could say that every term is equal to the term, the previous term, multiplied by 1/4. So we'd have 1, 1/4, 1/16, 1/64, etc. So you could think about how this sequence converges to 0. The limit converges to 0. For the last example, we're going to think about an application. So go ahead and pause the video and think about how you could describe the growth of this bungy tree, or bungy, I'm not actually sure how you pronounce that. If it is 7 meters tall today, and it grows an average of 2.3 centimeters per week. The 2.3 centimeters per week is arithmetic with a common difference of 2.3. 7 meters is 700 centimeters, so we have a rule for the nth term, and after 1 year, that would be 52 weeks. This is weekly, so we would have let a sub define the 50 a sub 52, so let n be 52, and you get 817.3 centimeters at the end of 1 year. Great job, everybody.